When we run an algorithm on a quantum computer, the result isn't just right or wrong. There's a much more nuanced question we have to ask. How truthful is the answer?
Truthful? That sounds intense.
It is. We're talking about how closely the final quantum state of the qubits matches the perfect theoretical state our algorithm was designed to produce. This concept is called quantum fidelity.
Okay, so it's like a world-class orchestra. They have the sheet music, the ideal, flawless performance, but what you actually hear in the concert hall is always slightly different.
That's the perfect analogy. A few notes might be slightly off-key, the timing a fraction of a second late. The sheet music is our target state. The live performance is our output state.
And fidelity is the score for how close that performance was to the composer's original vision. The difference between a standing ovation and just polite applause.
Precisely. In quantum terms, our sheet music is the final state our algorithm is supposed to create. But the quantum hardware, our orchestra, is incredibly susceptible to noise and imperfections.
What kind of noise are we talking about here?
We're talking about environmental interference, like tiny temperature fluctuations or stray electromagnetic fields. These things constantly disturb our delicate qubits in a process called decoherence. It's like a cough from the audience during a quiet violin solo.
Wow, so it's really that sensitive.
Extremely. Even the quantum gates themselves, the very operations we use to manipulate the qubits, aren't perfect. A gate might be designed to rotate a qubit by exactly 90 degrees, but in reality, it rotates at 89.99 degrees.
So all these tiny errors, the audience coughs, the slightly mistuned instruments, they all add up and they degrade the final performance, the final quantum state.
They do. And quantum fidelity gives us a single hard number from 0 to 1 to quantify that total degradation. A fidelity of 1 means a perfect match, a flawless note-for-note performance.
And a fidelity of 0?
0 means the final state is completely unrelated to what you wanted. It's like you gave the orchestra sheet music for Mozart and they played random heavy metal. The entire computation is meaningless.
So this isn't just some academic score. If your fidelity is too low, your quantum computer is essentially a very expensive random number generator. The answer it provides is completely untrustworthy.
Absolutely. This is why improving gate fidelity and extending qubit coherence times is the holy grail for hardware engineers. Pushing from 99.9% fidelity to 99.99% is a monumental leap in capability.
It's the difference between a great community orchestra and the Vienna Philharmonic. That last fraction of a percent is where the real magic and the reliable computation actually happens.
So, when you hear about a new quantum processor, the number of qubits is only half the story. The fidelity tells you the asterisk quality of those qubits and how well they can actually perform the complex music we write for them.
It's the ultimate measure of trust. Can we truly trust the answer this machine is giving us? In the quantum world, it all comes down to fidelity.